Hello, my name is John Lynch. I'm a senior software engineer with Side Effect Software, and this is a masterclass on the ocean tools in Houdini 16. So we've had ocean tools in Houdini for a few versions now. They were originally introduced in Houdini 12.5. The ocean was represented by a single ocean spectrum, SOP, and we're going to talk a lot more about what exactly a spectrum means, but it was a way to define the look of the ocean based on things like wind direction and wind speed. You could then feed that spectrum into an Ocean Evaluate SOP, and it could both deform geometry, like you see in the screenshot here, but it could also output simulation data, so velocity fields, sine distance functions of the surface, and points for flip simulation. When it came time to render, you would typically need to bake out a displacement map per frame. These could be fairly large, but they would basically be repeating tiles of texture that you could then use to displace a large grid, for example, to create a large ocean. On top of that, we had a texture-based foam solver, which would track areas of the ocean where foam was created and sort of would die out over time, and then this would be used to drive a procedural texture. We also had tools for driving flip simulations. These were things like splash tank, wave layer tank. So taking the data from the ocean and sending it into a flip simulation, we didn't really have anything in the way of tools for integrating those simulations back into the source ocean when it came time to render. So addressing some of these limitations was the goal of our re-architecture of the ocean tools for Houdini 16. So our overall goals were to improve the ability to choreograph the look and the timing of the ocean. This both meant the scale of the ocean in terms of the size and when, for instance, waves might come into the scene, when they might overlap. We wanted to reduce any of the tiling artifacts, so the spectrum creates a repeating grid of waves, and when you laid that over a large area, sometimes it was obvious that there was this repeating, this tiling going on. So we wanted some tools to make it much less obvious that that's the case. You can see an example of that here. We wanted to avoid per frame baking as much as possible. So if all you wanted to do was render a large ocean, you shouldn't have to bake out a displacement map for every single frame if you didn't want to. We wanted a better look for our foam, both in terms of the way it looked, the way it behaved when it was sitting on the surface, and the amount of space that you could cover without, again, showing any sort of tiling artifacts. Our flip integration tools, we wanted to not only be able to drive the flip simulations better, have them match the underlying ocean surface better, but we wanted methods for integrating the results of those simulations back into the ocean when it came time to render, so that you had a seamless blend between the simulated area and the rendered ocean area that surrounded it. While doing all this, we still wanted to be able to work with other renderers besides Mantra, and we also wanted to be able to output information to our new terrain tools, both for creating oceans for terrains and for also creating just sort of interesting looking patterns that would serve as a basis for more terrain work down the pipeline. So let's look at some of the new features in Houdini 16 and the ocean tools that let us achieve these goals. There's a new layered architecture, and essentially that means that you can layer as many spectra on top of each other as you want when you're rendering your ocean. So instead of having just the single spectrum, the single grid, you can have an arbitrary number of these combined together to give you the overall ocean look. There's more control over the actual shaping of the spectrum itself. You can offset them in space and time. You can actually scale time, make some of them appear like they're moving faster or slower. There's also volumetric masking, so you can draw masks to limit the areas where a particular spectrum might have an effect. There's animated noise built in, so it sort of looks like that kind of, you can actually see an example of that also here in this scene here. Looks like that sort of patchy wind motion over the ocean surface. We have what's called wave instancing, where you can scatter points onto a grid and then render patches of the ocean on those points, and they can all have sort of a random offset of orientation, amplitude, and again, that's what you're seeing in this render, which helps reduce timing as well as, reduce tiling, as well as has some special effects that you can sort of do by for instance, aligning the ocean along a particular grid or curve within the scene. So we'll see some examples of that later. We have the ability to choreograph hero waves, which means very large waves that might come into the scene at a very specific time that need to hit a boat or an object or whatever to sort of establish a beat in the shot. We can also do render time evaluation. So instead of having to bake out displacement maps, you can save out this one set of spectra together, this one set of layered spectra, and then render that anywhere sort of in space and time within Mantra. We've improved the particle foam. The solver actually is now a particle foam solver. So it's a particle simulation that can both have a better look, and it will also cover a larger area of the ocean without any of the tiling artifacts from before. We still have the ability to bake out all of these layers to render with different renderers if we need to, and we can also output them into the terrain system. And then finally, we'll look at, and later in this class, how all of these tools work together to make it easier to integrate the results of a flip simulation, both to drive the flip simulation better, but then more importantly, to integrate that simulation back into the surrounding ocean when it comes time to render. Houdini 16 has an entirely new layered architecture for oceans. To enable this, one of the things we've done is completely rewritten the evaluation code for oceans in VEX, which is the internal shading and computation language for Houdini. It's located here. You can see in this location within the Houdini installation. And if you're a very sort of advanced TD level user and understand or are comfortable with VEX, you can actually see how all of this is implemented. But implementing it this way gave us a lot more flexibility for being able to handle as many of these layers of oceans as we wanted to. So there's arbitrary layers of spectra that can be just merged together. So you combine these with a merge SOP to define the ocean. Then you can basically save out that set of combined spectra, and that geometry will define the ocean. And you can use that geometry for rendering. You can use it for simulation. So you could have, for instance, one user that would actually define the look of the ocean, and then they could sort of send, just by sending this file, this one single file, downstream in the pipeline to, say, an effects artist, who could then do simulations based on top of that defined ocean, using the exact same look that was done sort of in look dev earlier in the pipeline. Another advantage of having this evaluation done in VEX is that we can actually do ocean evaluation entirely within a single VOP. Now we can't create all of the data, that Ocean Evaluate SOP will. So we're not trying to create all the volumetric information to drive simulations, for example. But the sort of key data outputs of the ocean evaluation, which are displacement, velocity, and cusp, can come from that VOP, which means that we can do ocean evaluation at render time. So this architecture sort of all works together to both consolidate all of the ocean definition into one file and allow us to evaluate that file at render time, or really from any VOP context. So I've been talking a lot about an ocean spectrum, and I wanted to back up a little bit and describe exactly what we mean by that, especially since the ocean spectrum has existed in the ocean tools in Houdini since they've been introduced. And then I wanted to explain what they are, and then go through in the viewport ways you can sort of visualize how exactly you can use that to control the look of an ocean. And I also wanted to describe some of the features that are new in Houdini 16 for creating spectrum in the first place. So a spectrum is essentially a measure of the amplitudes of a bunch of waves of different frequencies. And you can actually see in the bottom right-hand corner of this slide what a visualization of a spectrum might be. So essentially the different colors represent how strong the amplitude is for particular waves within that spectrum, and in particular directions as well. So the idea behind these type of ocean tools for a single spectrum is we procedurally generate a set of frequencies that correspond to an ocean of a particular depth, with wind moving in particular directions, and then some other parameters as well that you can control. We take all of that data, generate a set of amplitudes for all these waves, and then using what's called a Fourier transform, turn those into actual displacements that you can then apply to a grid in sort of world space. So this method of creating an ocean is sort of frequently referred to as a Tessendorf-style ocean, after Jerry Tessendorf, who sort of popularized this idea within graphics. And it combines both a physical model for the speed of the waves and dispersion. And what that means is within an ocean of a certain depth, there is a relationship between waves of different frequencies. Typically, the very large, sort of low frequency rolling waves, big roller waves, move much faster than the small choppy waves. And that look that you see is very particular to deep water oceans. So there's a physical relationship there between the waves, and those are typically just functions of the depth of the ocean and the amount of gravity. But then that doesn't, if that's all you had, then you're really just defining the relationships between the different waves. You want more control than that. You want to be able to say, well, I've got an ocean that looks like there's been a prevailing wind in a particular direction, and it has, very sharp waves that follow exactly this wind, or maybe it's more of a diffuse look where the waves are moving in all sorts of different directions. So on top of that physical model, there's a statistical model. And the statistical model is created by a set of oceanographers who basically take lots and lots of ocean data and they do model fitting to various wind conditions so that they can essentially come up with a mathematical model for saying, okay, if you have wind pointing in this particular direction, then typically you're going to see a predominance of waves moving in this particular direction with these particular frequencies. So it's the combination of this physical model of speed and dispersion and this statistical model that then allows some control over what this ocean is going to look like. So the ocean spectrum SOP is what allows you to create this spectrum. We represent that with three 2D volumes. And these are Houdini native volumes, but they're just two-dimensional. There's one that represents the amplitude of the waves, one that is the phase of the waves, and then the angular frequency, which you can think of as the speed of the waves. These are all combined in that evaluation code that we were just discussing earlier to create coefficients for this inverse fast Fourier transform. So you take those three volumes, and then you can turn them into these coefficients that will then actually generate the physical displacements for the grid, and you can do that sort of anywhere in space and time. We also are going to attach various attributes to these volume primitives for things like the choppiness of the waves, how much they sort of peak in the middle, whether or not there's any noise applied to them, and there's a series of other attributes that we'll look at later. So combined, these will all sort of create a particular ocean layer that, as we've said, can then be combined with other layers to create the larger ocean. The spectrum doesn't actually do any deformation. That's important to remember. It really is just creating data. So that spectrum has to be evaluated either by the Ocean Evaluate SOP, or in Houdini 16, it could actually be evaluated by this VOP, as we discussed for render time evaluation, or really evaluation in any other context. So there are a few new features for the ocean spectrum in Houdini 16. They've been highlighted here, but briefly, they're just you can offset the center of the ocean, and you can actually scale the time of the particular layer. So this can be useful to maybe blend between, using a mask or something, between two different oceans, possibly even of the same kind, where one's moving faster than the other. There are high and low pass filters, which starts to become very important when you want to combine, for instance, flip simulations or simulations that have been driven by just maybe, say, the big low frequency waves of an ocean, but you want to combine that with the surrounding ocean that has all the high frequency data as well, and we'll look at ways to do that. You can apply volumetric masks and noise. There's the animation that's playing in the right-hand corner is the animated noise that is built into the ocean spectrum now. And it also has support for the wave instancing that we talked about, where basically you're instancing patches of the spectral ocean onto points, and they'll be oriented according to the typical Houdini copy and instance attributes of those points. So now let's jump into the Houdini viewport, and we'll look at ways you can visualize and sort of maybe get a feel for how these different parameters combine to control the look of an ocean. So this is a setup where we've got an ocean spectrum SOP feeding into an ocean evaluate, and we're just going to look at how the visualization options on ocean spectrum let you get sort of an instinct for how the wind parameters are going to affect what the spectrum looks like, and then in turn what the resulting ocean looks like. So in the visualization tab, we've just got spectrum selected here, and as we in this visualization, the thing to remember is that in the middle here, this represents the lowest frequency waves, which are typically the kind of big roller waves. And as you move further away from the center and around this circle, you get to the higher frequency waves, so the smaller, choppier waves. And where they are on this circle corresponds to the direction. So all of the waves are present here. The question is just sort of, do they have any amplitude or not? All the waves along here, for instance, along this x-axis are moving in the x direction, and then this statistical model that we were talking about gives them different amplitudes based on the direction of the wind and these bias and movement parameters right here. So the easiest way to see this is as we change the direction, the wind direction, you'll notice that what this model does is it essentially depresses the amplitudes of all the off-axis waves. So all the waves that aren't in the direction of the prevailing wind get set to 0, and the ones that are in the prevailing wind direction get set to sort of a random a value that is based on their frequency and then some randomness defined by this random distribution parameter here. So if we reduce the directional bias and movement real quickly, what you'll see is we get just kind of a big random set of amplitudes. And as we change the direction, it doesn't matter anymore. So we're essentially saying that we've got a big ocean where the wind is moving in every different direction. And if we take this grid and we're creating a GL lit attribute on it, and all that means is we're applying the OpenGL lighting in the viewport here. So we're actually going to deform this visualization itself, which can be kind of an interesting way to view things. And if we play this, you'll notice that there's really no direction here. We've got sort of a bunch of waves that are moving in every different direction. It's like as if the wind were blowing in all directions at once. And the strength of the wind does matter. So as we increase the speed, we will see that we get these larger low frequency kind of roller waves. So we're affecting those innermost low frequency waves by the speed, but we don't have any control over the direction. And the same thing, as we reduce the wind, we'll see that all these low frequency waves start to go away, and we just get ripples. We just get all these high frequency ripples, and that's what we're seeing in the spectrum as well, is just these higher frequency around the outermost part of the circle. So if we go back to defaults on directional bias and movement, what we'll see again is, this as well. So the bias is essentially determining how big this lobe is. How much does a particular wave have to be aligned with the wind direction to get any amplitude? So as we increase that, you'll see that we're essentially making this lobe here narrower. So only waves that are very much aligned with this wind direction are going to get any amplitude at all. And if we view what that actually looks like, you'll see we get these very sharp sort of aligned waves here that are moving all directly in the direction of the wind direction, and we don't get many of these sort of off-axis directional waves at all. So we get a lot of control over exactly which direction we want the winds to move, just the waves to move, again, because we're suppressing all of these waves in the other part of the spectrum. And similarly, this directional movement corresponds to, there's always, for any of the waves that move in this direction, there's a corresponding wave moving in the opposite direction. And how much we want to suppress any of those moving in the opposite direction is what this directional movement is. So you'll see as you decrease that, you actually get waves that are aligned with the wind, but there are actually some that are kind of reflecting backwards towards the wind direction and some that are going with the wind. Typically, you're going to want this, you're going to want this set higher so that the waves do actually move along with the wind in the same direction. So hopefully that gives you some feel for just the overall controls for what the wind is doing. All of these wave frequencies are always existing in the spectrum. It's just a question of which ones get their amplitudes boosted and which ones get sort of scaled down so much so that they essentially don't have any impact on the look of the ocean at all. So let's sort of go back to defaults here and look at some of the other controls, some of which are new. In particular, the filtering ones. So these filters, there's always been the ability to limit the minimum wavelength. So really what that does is removes the highest frequency waves. which is useful. And again, if we look at what this looks like deformed, as we increase the minimum wavelength, so we're decreasing the highest frequencies that we can see. We see that we start to lose all these high frequency amplitudes, and also in the deformation we can see that we're left with just these nice smooth low frequency deformations, but there's no detail here. But what's new is this filter above and filter below resolutions. And so what this lets you do is do a similar type of filtering, but actually do it in terms of this same resolution exponent that we see here. And this is mostly useful for combining spectra. So if you've got one spectrum that has all the, for instance, low resolutions like this one, and you want to feed it into a flip simulation, and then you want to add in just the highest frequencies that were in this spectrum so that it matches, say, the entire spectrum, which is used for the surrounding ocean, you can do this with this filter below resolution. So in this case, you can see we're essentially just chopping off all the low frequencies here, and we get just this high frequency section here. So if we turn this on, and I think this is set up, yeah, so this is set up to have essentially all of the low resolution, low frequency waves that we've just removed from this one. And so you can see they're essentially sort of inverses of each other. And then if we merge these two together, we basically get back to our original, ocean. And if we disable that merge, we're essentially just going back to only this one layer. We lose all those high frequencies again. And again, you'll see why this becomes important as we want to integrate flip simulations, which tend to have just these lower frequencies, into a surrounding ocean where all the frequencies are present in the surrounding ocean, and we want to apply just the high ones, just the high frequency ones to this simulation area. And then finally, another feature that's in 16 that's new is masking and wave instancing. We're going to talk about wave instancing in some detail in a second, but for masking, one of the simplest ways is to add noise. We're going to actually visualize our mask real quick. And what's interesting about this noise, it's set up to have this kind of large-scale, kind of patchy look here, to represent kind of sort of windy areas within wind sort of blowing over the ocean. So it's actually got this animation built in, and so if we look at the noise parameters, it's also got a direction, just like the ocean does. So we can actually animate which direction the wind is blowing, even if that's if we want the sort of patchy gusts to look like they're in a different direction from the overall wind of the ocean, we can do that. It has size parameters that are different per axis. So you've got sort of how big are the patches along the wind direction and how big are they across the wind direction. And then sort of standard roughness and turbulence and speed, just sort of how you can have them just evolving in place, or you can have them moving along. And then same thing with pulse length. They can either move or they can actually evolve as well. And offsets and stuff, and also input range, so you can map kind of how much of an effect this is actually going to have on the underlying amplitudes of the waves. And one thing that's nice about this right now, so I've got the time dependent badge up and viewed, and if you notice, we've got right now it's time. This ocean spectrum node is time dependent, which means it's changing, it's recooking every frame. But that's really only because of this visualization. If we turn that off, it's no longer time dependent, which means that even though that we've got that animated noise that's being applied to this grid, this is actually static data, which means that we can write that out once, this layer once, and that noise will actually be animated every frame because it's actually represented by properties on the spectrum itself. So let's look at that real quick. So this is the geometry spreadsheet. So these are these primitives that we talked about. These first three are the 2D volumes that I was describing that make up the spectrum: phase, frequency, and amplitude. And then these are the masking ones that we'll talk a little bit about. But essentially they're volumetric masks, and then the point mask is the one used in wave instancing. But if you look at these noise values here, noise enabled, noise offset, all of these various noise direction, all these various values, That's what we're changing when we set these parameters. So as we change the direction, you can see that the noise dir is updating. We can turn noise on and off. So really, these are just this tab here is just setting those parameters. It's not actually doing any animations, just setting the parameters, and then the Ocean Evaluate or the Ocean Evaluate VOP, however you end up evaluating the spectrum, will actually read these parameters in all of that VEX evaluation code that we were looking at earlier, and will apply the mask and apply the noise at evaluation time. So you can write out this spectrum once, or multiple spectra, with this animated noise, and it will show up as an animated as a moving noise that evolves and moves over time. You can sort of see that here, even though this spectrum itself is not animated. Wave instancing is one of the most important new ocean tools for Houdini 16, and this is a technique for instancing patches of that spectral ocean onto points. And these points will have various attributes that obey the typical copy instance attributes of Houdini to orient those patches of ocean to scale up their size and generally give a lot of control over which direction these waves should be facing, or possibly even moving. There's a set of parameters on the Ocean Spectrum SOP on the Wave Instancing tab that let you set the parameters that control the look of these patches of ocean, as well as randomize them. So it makes it easy to create large sets of points that give a sort of overall random look to these patches. There's support for both 2D and 3D sets of point clouds. 3D would give you an example like this from the Houdini 16 new features video. There's proper rotation of velocity and cusp, which is important both for rendering. So as you can see here, you've got cusp sort of pointing in the right direction, that peak on top of the waves. But also, if you are using the wave instancing and then want to send the data into, say, a simulation, we need to make sure we have proper point velocity. So we'll look at how we get that. And this is a technique that's really useful for infinite oceans, so reducing the tiling that we were talking about earlier, where you could instance patches of maybe 3 or 4 different spectra if you wanted to onto points across a large grid, and it makes it very, very difficult to tell that there's any sort of repeating going on. And in fact, the large ocean shelf tool uses that technique, and we'll go into that later. And then you can also do special effects like these sort of deformed oceans here, either in 3D or in 2D. So let's look at what that looks like in the viewport. So here's a very simple setup of wave instancing in Houdini. What we have here is an Ocean Spectrum SOP, and it's plugged into Ocean Evaluate, and it's deforming this grid as usual. But what's different is, so Ocean Spectrum with Houdini 16 now has 2 inputs. The right input is that volumetric mask that we've been discussing. This left input is for the wave instancing points. So these are the points that you would instance the patches of ocean onto, and it reads the attributes on those points and copies the patches similar to the way like a copy to point SOP works. So here we've got just a very simple point at the origin, and if you look on these, so here are the wave instancing parameters, and we'll go through these in a second. But I've got the variance, the randomness turned all the way down, and so if we look at the way that we're deforming this grid, if I remove this point, you'll see it's essentially the same thing. So all we've done is instance this patch of ocean onto this point within a given radius. So and I can increase that and decrease how much, basically how big that radius is going to be, how much of an effect it's going to have over this grid. As we start to vary or return some of these values to their standard defaults, you'll see that, for instance, the offset, as we change the offset, that controls where into the patch of ocean the lookup occurs. So this is going to be different for each point, and this is part of how we get the randomness and the variation and get away from that sort of tiled look, is because each different point is going to be looking up into a different patch of the ocean, of that larger ocean tile. And so just quickly we'll reset all these. So what you'll see is that we have variation on amplitude, the rotation, so I can change the rotation, and that just rotates the underlying ocean. So you'll typically, the way you'll do this is the ocean spectrum itself, and this is the spectrum that's being instanced onto this point. You'll leave the direction at aligned along the x-axis, the wind direction. You can still change the bias and movement however you want, but then the individual rotation will typically be controlled with point attributes. So we can move these all around and control things like the roll-off, the fall-off of how quickly the edges of the area of this radius will get deformed by the ocean, and seeds, and all these seeds just correspond to these variance values. So as you change the seeds, you're changing different offsets, you're getting a slightly different rotation, that sort of thing. And these become really important as you start to have more points. So let's switch to a slightly different setup. We're just scattering points here. We can start off with one. And we're going to do what we did before, where we're actually going to be visualizing the wave instancing points here, and we're going to send the actual visualization into the ocean spectrum SOP. So here you can see we've got kind of a fall off area here. It's a little hard to see, but this is the z-axis and then up, of course. And you'll see that this is really what we're controlling by the rotation. Is we're controlling the local frame here that we're instancing the patches onto. Let's reduce that a little bit. And then as we add more points, so let's maybe go up to 5 points or a few more, we'll see that they're starting to overlap. And they've each got a little bit of variation in their rotation. We can increase that amount of variance if we wanted to in the rotation. So you're seeing that they're just going to be offset a little bit more. And what we're seeing as we look at this is we're starting to see an ocean that has or a grid that has a fair bit of variation in the sort of local direction of the waves. This may actually be a little bit too much, but you can see as you would vary that over a very large grid, you can essentially, there's no indication that these are necessarily coming from the same patch of ocean, especially as they start to interact. And as we increase the point count, you can see more and more. And as they start to overlap, you'll get increases in the amplitude. So you have to be a little bit careful with that. And you can just decrease the overall amplitude for all the points here. And again, they're getting some randomization on the amplitude values through this variance setting as well. So closely related to wave instancing is the Hero Waves feature in Houdini 16, which is created with the Ocean Waves SOP, which is a new SOP. And the Ocean Wave SOP creates another ocean spectrum, a specialized ocean spectrum. In this case, it actually has spectral values of amplitudes of 0, but it has some attributes set to tell it to instance these sine wave bumps onto each point. And you can combine these points along, say, a curve, for example, to create a waveform, and then animate that over time, and that gives you sort of this hero wave look. So if we start this animation playing, you can see this is a spectral ocean layered with ocean waves. And these ocean waves, this is actually along a curve. We'll look at this setup in just a second, but there's a curve here that's just being animated through the scene and instancing these hero waves on top of it. So just like the regular wave instancing, it obeys the regular copy instance attributes. You can either input custom geometry like these curves, or there's actually a waveform and even a wave train generator within the Ocean Wave SOP, which lets you, if you just want to say create 5 waves sort of moving in a general direction of a certain size, it can do that for you. It will calculate velocity on incoming animated points, and then it will in turn transfer that velocity to the underlying ocean based on the wave shape. So again, just like with the wave instancing, if you want to feed this type of ocean into any of the simulation tools or get motion blur from it or anything like that, you'll get proper point velocities from these instanced hero waves. Proper cusp values also, as you see, and typically these are used along with spectral oceans. So by themselves they look a little boring. Again, we'll see that in a second. But combined with spectral oceans, you get this kind of overall nice look of the small, choppy, high-frequency waves done by the spectral part of the ocean, and then these very large, these are probably 5-meter tall waves, instanced along the hero waves here. Okay, so let's look at how we would use the ocean wave SOP to create these kind of hero waves. So we're going to start off with a very simple setup again. We've got another point just at the origin here. Actually, let me turn this guide off real quick. So we're just creating a normal attribute on it that's pointing along the x-axis. Right now we've got a transform on it, although we're not transforming it anyway, and then we send it into this ocean waves SOP. The ocean waves SOP is, again, it's really a specialized version of ocean spectrum. It creates a spectral ocean that is with zero amplitudes, and it actually sort of renames some of these parameters that are on the wave instancing tab to kind of make it easier to control creating hero waves like this. So what you see here is this kind of sine wave bump that I was talking about. So you use similar controls to what we did with wave instancing. You can control the radius of this bump and fall off and that sort of thing. The amplitude, as you're seeing, we're getting cusp values as we feed this in. We're just feeding this into a regular ocean evaluate here for the deformation. You can rotate the individual points themselves, change the width of how big this wave is going to be, change chop on a per point basis, this sort of thing. So this is just for a single point, and typically you wouldn't really use it with one point. You'd use it with a series of points, like along a curve, as we'll see in a sec. And you notice we have cusp values here, but we don't really have. I've actually got point trails on for velocities. We don't have any velocities, and that's because we're not. This point isn't moving. So if I move through the timeline, nothing's happening. So we can rotate this point around. We can move it around in the plane, and it'll move that bump. But we can also animate it. So to do that, let's say let's just make a little expression. And let's see where it went. There it is. So now you can see that because we have an animation, it's doing this central difference computing velocity. It's basically a trail SOP internally. This is just an asset, as you can imagine, a Houdini digital asset. And then the transform, since it's moving it now, we're calculating velocities on this incoming point and then transferring those to the sine wave. And if you've ever done any sort of work with like derivatives of sine waves, calculus of sine waves, taking the spatial derivatives, which is what gives you the cusp here, or the time derivatives, which is what gives you velocity, is pretty easy with a sine wave. And to just adding up a bunch of sine waves, you just add up all the derivatives. So that's how we can calculate these values, no matter how many of these things we have. So that's just with a single point. So let's look at something a little more interesting. So here we've got a curve a very simple curve I drew. I resampled that just to give me how many points I want. In this case, we've got 6. And then we use the polyframe SOP, and we're basically making a normal. Not positive, if I'm able to see this or not. Yeah. So the normal is really facing along the direction of the sort of trough of the wave, which is what we want here. So the bitangent is typically what we're going to use here, and that means that the individual bumps of the waves are going to be aligned along with this. So we transform it a little bit just to give it a little rotation, and then we do a copy to points. So this actually is, we're just taking another big line here and copying each of the curves onto that line, doing a little animation just like we did before, and then sending it into the ocean wave SOP. And so if we use this one for our deformation, we'll see that, just turn off these visualizers, we get these kind of simple, it's actually, you'll see underneath each of these curves, we're getting this deformation. So these become our hero waves. And if we just want one, we can get rid of the copy to point and just have one wave that comes through. And so we've got, again, these there's variation, there's some variance on the rotation. So each of these instance waves is actually slightly rotated along the normal. So you'll see that as we change this shape seed, you can actually get slight variations. And you'll notice that all of the it's a little hard to see, but all the different waves, even though they're not even though they're based on the same curve, they have slightly different shapes, and that's based on this variance, which you can see here as they're kind of. And you can turn these variance values up if you want to get more variation. even from the same source. Again, this is a little dull looking. So all we really need to do is merge this with a regular spectral ocean to get something a little more interesting looking. So that's what we're doing here. So this is just a regular ocean spectrum, and we merge it together with the spectra that are being created. This kind of empty spectrum, but with with the ocean wave instancing, to get something that looks like what we saw in that rendered video before. So they're really effective to add together. By themselves they don't look like too much, but they look like a nice hero wave when you add them all together. And then the other thing that the Ocean Wave SOP can do is actually create waves for you. So if all you want to do is sort of have a bunch of waves aligned in a specific direction, so let's see if we can. What's invisible? Yeah. So all this is doing is creating some animated lines for us with these, and then it's feeding them through these various shape attributes. It's actually merged with anything that is input. So you can input custom geometry and have the wave train generator working at the same time. So it's just how many waves do you want, how many points per wave do you want, their horizontal size, how far apart they are from each other, direction, speed, and you can do it either with an animated wave speed, or you can actually just animate the center, and you can put an animated expression in here as well, whichever way you'd like to do it. And then, so if you just want a set of a wave train, or sort of a set of aligned waves coming in a certain direction, a certain speed, but you can get that variation from both the jittering the points and then the shape variance as well. This is an easy way to generate a bunch of waves that way. And then one thing you'll notice here, and I'll talk about this more in a second when we go into rendering, but you actually have a split SOP here, and we're sending two different outputs. We're sending both the spectra, and by that I mean those. Here, let's look at that real quick. That what's in here is just the phase frequency amplitude. So this is created by the ocean waves. These first three, they're going to be basically empty and won't take up any memory. And this next three are going to be created by this. And then the mask just has the point mask and mask primitives. So the reason we're splitting these up is the spectra, like we were talking about before, doesn't change at all. The spectra is static throughout the entire frame range. It can be evaluated anywhere in space and time. The mask, because it comprises both any volumetric mask but also the points that represent these waves, they are animated. They're moving over time. So you can actually probably see that. Yeah, so we can see that these guys are actually the points are moving as we scroll through. So what we're going to do is actually save them to different sets of files. And the reason we do that is you can do this with save current frame. You just need to save this once. And then the maps, you actually save the masks. I'm sorry, you save for every frame. And the reason you do that is if you look at the resulting file sequences. So this is ocean waves. I called it maps. I was wrong. This is a mask, but it's about, so the entire sequence is 1.6 megabytes for 240 frames, and the spectrum is about 2.5 megabytes. So total, you're looking at maybe 4 megabytes worth of data for this entire frame. Whereas if you were saving the spectrum each time, it would be 2.5 megabytes per frame, even though it doesn't change. So these separate spectra and mask outputs can actually be used in the shader that we're going to look at in just a second for rendering, and that's in fact what I did to render that sequence that we saw with the slides at the beginning. I wanted to quickly go through a few more examples of setting up layered and instanced oceans. This is actually a file that has several examples in it with some sticky notes and stuff, and all these files are going to be available with the Masterclass. But I just wanted to show us a couple of the examples because they show some sort of interesting techniques. So let's bypass this for now. So these two spectra are actually tied together in a way. So this spectrum has noise and has a contribution mask. So basically that means that all of the noise here will contribute where there are waves from this spectrum. And then this one is actually set to blend with the spectrum. So, and it's pointed at this one over here. This had spectrum 4. Easier to see. So anyway, what this will do is it'll actually grab all of the values, the noise values from spectrum 4, and use the complement of that. So this becomes a really simple way to blend between two spectra just based on noise. And again, because the animation is built in, this is a static set of geometry, but it has sort of an animated blend between these two spectra. So if we look at just one of them, you'll see there's these kind of blank spots here, and they exactly correspond to the spots that are not blank that actually have waves from this other spectrum. And when you combine them all together, you don't have any blank spots, but you have a blending between the two different spectra according to these noise patterns. And then on top of that, we can just add some bigger waves if we want to. And then this other example, so this is an example of here. I'm going to show you a render in a second because it's hard to see in the viewport. But this other spectrum here is just a reference copy of this original one. But they again have the same noise masking idea, where they're blending between each other. And this one has a high pass filter on it. So they're the same ocean, but one has has a bunch of the high frequencies removed, and it'll blend between those two as these sort of patches of wind sort of blow through an ocean. If you've ever seen it, there are these kind of areas that look smooth and areas that look kind of real choppy because of as these little gusts of wind move around. So if you look at a render of that, you can sort of see here you've just got these real high frequency areas, and then these kind of areas over here where it looks like it's just been kind of smoothed off. And in motion, these areas kind of move around. So just kind of an interesting way to blend these two filtered spectra together. Here's an example. This is a real simple example of masking. I just don't think I've shown the actual volumetric mask before. So this is a very simple, just creating a density field from a torus, and this can be animated or whatever, but the idea is you've got a mask, and if you look at the actual spectrum resulting from that, whoops, we're not doing that yet, sorry. You can see that in this case it's a suppression mask, so nothing is anywhere that torus is, we're not getting any waves. If we change that to a contribution mask, that basically inverts that. And then there's some examples of wave instancing which we've kind of seen, but this is kind of interesting. So this is a setup where we take a curve, and again we resample it. Although now when we're resampling, we're creating a tangent attribute, and we're just setting it to the normal in this case. Don't think those are going to show up, but there's a normal attribute that's following along this curve. Then when we show that, when we deform with a grid with that, what we see is we basically have an ocean that's aligned along the curve. So again, there's no animation. It's moving a little slow here, but you can sort of see if we speed it up. There's no animation built into any of these attributes here. This is static geometry with normals, but because there's animation built into the spectrum as it's aligned along the curve, it sort of looks like it's kind of flowing along this curve in some ways. And obviously you can control the spectrum to sort of look however you want. And a sort of similar idea is to create radial normals. So in this case, we're just taking a grid and scattering a bunch of points on it and creating radial normals. So basically, this is real simple. But just we create, basically they're aligned along the circle around the grid, and then we use that to instance points onto ocean patches onto it. And if we display that, we get sort of this whirlpool effect. Again, there's no animation here. It's just the ocean is moving along the x-axis, which in this case has been oriented along these radial normals. So you get this kind of whirlpool. And I actually have a render of that real quick in motion. And so you see the same sort of thing. Again, there's not any animation here. This is a static set of spectrum geometry and mask. But because of the animation built into the oceans, you get this kind of cool radial whirlpool thing going. So let's talk about rendering the oceans that you've created now with Mantra in Houdini 16. One of the biggest changes is we now have render time evaluation of spectra. So you create all these layers. Maybe they have masks. Maybe they're animated masks. Maybe they're static masks, like some of the setups we saw. And it's time to render those. In previous versions of Houdini, well, one, you couldn't have all the layers and masks, but no matter what, you had to bake displacement maps. So you had to bake out the texture, and then you would use those textures to displace like a grid and render that way. So in Houdini 16, you only need to save out that spectrum geometry that combines all the various layers, masks, that sort of thing. And then the ocean sample layers VOP will actually read that. It uses one low-level function that we're going to look at in just a second called ocean sample, which is pretty much the only new C++ code in this whole architecture that can actually do render time evaluation of these spectra. So actually create the coefficients, the FFT coefficients we were talking about, and do the inverse FFT to create the displacement or velocity or cusp at render time. The ocean surface shader has been updated to use that render time displacement, as has the ocean volume shader. So we're still using an interior volume, uniform volume, to do absorption and scattering underneath the surface. So typically when you render, you'll render a grid to be the actual displaced surface, and then you'll do a volume underneath it, a box or something that'll be a uniform volume rendered with the ocean volume shader, and we'll look at an example of that. It has automatic anti-aliasing built in, and what that means is because we literally know the frequency content of everything that we're trying to render because we're dealing with spectra. So we can essentially downsample the spectrum as we get to distant parts of the render where we don't have enough shading samples to resolve the tiny little waves that are in a given spectrum. So we can basically calculate that during shading and just downsample to use a lower resolution version of the spectrum, just like we would in Ocean Evaluate, where you can set the downsampling parameter. There are separate inputs for the spectrum and mask, and we saw an example why you might want to do that in the ocean waves example, and we'll see some other ones when we look at a flip integration. There is procedural foam from the particle foam solver, which from a point cloud. So that's kind of what these things look, these patterns through here, these foam patterns. And actually, we see several of these at work if we play this animation. So in the distance here, you're seeing the automatic anti-aliasing, you're seeing the procedural foam. This is basically the large ocean shelf tool at defaults. It has obviously a camera move and a boat in it, but besides that, this ocean setup is the large ocean shelf tool. So it's scattering points onto a very large grid. I think it's an 8-kilometer grid, and then instancing patches of ocean onto that, and then we're running the foam shader on top of that, or the foam solver on top of that, and then feeding it all to the ocean surface shader, and then doing render time evaluation of the oceans. And then finally, I wanted to talk a little bit about combating some rendering artifacts that may show up that are typically the result of just using too low resolution spectrum, and how you can combat those. So I wanted to describe the new ocean sample vex function because it's what allows the render time evaluation of spectra, and it's new in Houdini 16. It's a fairly low-level function that you may not run into much, but I think it's worth looking at to sort of understand what it's doing and what it allows us to do in terms of evaluating spectra from really any vex context, not just rendering, but shading or SOPs or anywhere. So if we look at this function, and actually this is the help for it. So you pass in geometry and then primitive numbers that represent the phase, frequency, and amplitude, those 2D volumes that we were looking at earlier. H scale, horizontal scale, that's basically just your chop parameter. The current time. Mode is just one of whether you want displacement, velocity, or horizontal derivatives, which turns into cusp. Whether you're doing any downsampling, and where you want to sample the resulting ocean value, whether the ocean displacement, for example. So this is an example, and this example is basically what we're doing here in this wrangle. We're just passing in the input geometry. The first 3 primitives, which I happen to know coming out of a spectrum, are phase, amplitude, and frequency, the chop, and these various settings. And if we do that, So we're getting displacement here, and we're just offsetting the position by displacement. We essentially get our deforming ocean. And this is kind of the simplest use of ocean sample. So just to make it slightly more complicated, all this is doing is exactly the same thing, but instead of just getting displacement, it's getting velocity, point velocity, and also the spatial derivatives, which we can use to calculate cusp. So when I was describing the vex code, this ocean.h, that's the vex code that we talked about at the very beginning of the class, and it has a bunch of sort of convenient functions in it. One of them is if you have the spatial derivatives of all the different waves, and you want to compute cusp, that's what this does. And then we're offsetting the points by the displacement. We're setting the point velocity, and then we're setting a cusp attribute, which we have a viewport visualizer on to show to us. So again, a very simple use of the ocean sample function, but it shows how you can get these kind of low-level values out of the input spectrum. So just to get a little more complicated, this is basically the same code, but we're inputting multiple spectra. So now we've got 3 of them going in. I happen to know that there are 5 primitives in each one, so we're just figuring out how many layers we have by looking at the number of input primitives, figuring out what the primitive numbers are for each of our input volumes. And then we're combining the displacement, we're adding up the displacement, the velocity, and the derivatives, and then we're doing the compute cusp again. So if we do this, you'll see that we get a much, we've got all 3 of these spectra that are input, and as we sort of turn them on and off, you can see that we're actually getting all of the effects of all of the spectra together. So the only issue here is, so this works pretty well, but it doesn't really give us any of the wave instancing or any of the noise or masks or anything like that. So for instance, if we go to all of our spectra and we turn on noise, nothing happens here, and that's because there's nothing in this low-level function to handle any of those noise inputs. It's all in that ocean.h vex code that we talked about before. So for instance, this attribute VOP does support it, and that's because if we go inside that, it's actually using this ocean sample layers VOP here, which is also a new VOP, and it is that ocean sample layers calls that ocean.h code, which ultimately calls ocean sample, but on top of that it layers noise and masks and does the instancing and all those sorts of things. So this is what gives us full support for everything that the spectrum does, is running it through this ocean sample layers VOP. There's also an ocean sample layers vex function in ocean.h that this calls if you want to do that directly. And then finally, just the other way that you can use that VOP is if you actually output the rest displacement, rest velocity, and rest derivatives. So what's happening here is we're actually evaluating the spectra, and we're just putting them into rest position volumes. So these existed in previous versions of the Ocean tools also. But because we've already evaluated these, instead of having to call ocean sample, we can just sample from these already evaluated volumes. And that's what this does as well. It just gives us the same result. But internally to ocean evaluate, when it's calling the vex code, it's usually doing this. It's already calculated the rest values once, and then it just layers them all together using the ocean sample layers VOP. So the overall rendering workflow hasn't changed too much. This is the on the Oceans tab. We used to have an Ocean Waves tool. This is now called Small Ocean, just to distinguish itself from Large Ocean. Small Ocean is similar to the pre-Houdini 16 Ocean Waves tool. And it puts down a spectrum, puts a merge stop down there so you can add as many other spectra as you would like, and just sort of gives you a preview grid like usual. The one major difference here is that instead of baking out, so this is in Ocean Evaluate 2.0, which is what this is. You can still export to texture, but all you're getting is the spectrum data. You're not getting any of the masks or anything like that. So what you really want to, in general, we're going to actually talk about a way to get around that. But for the most efficient use of disk space, what you really would like to do is just write out the spectrum geometry itself. So as many spectrum masks layers as you've got, you write it to one single render current frame. So you write it once. And then when you render, it actually evaluates this spectrum at render time, again, at any point in space or in time. And it doesn't have to bake out each of those individual displacement maps that you had to do in previous versions. So just to show what this looks like rendered, this is with a little a boat for scale and with also the foam on it as well. So this is what just the result of the default ocean waves tool looks like. We'll go through how we do the foam in the next section. And if we go look at what has been updated, so if you've ever looked at these are all everything's now material. So with the new shading workflow in 8.16, they're not in the shops, they're materials.